So the layout of the rest of this lecture is as follows. So to begin with, I'm going to go through this big data example. So this is interesting anyway, but it's also interesting because it comes from a genuine industrial collaboration within the electricity industry. And the second part of the lecture, we're going to go through a small data example, which is primarily designed to be conceptually interesting, but it's really a sort of college type example rather than one that stems from a genuine industrial application. However, one thing I did want to mention here with this second problem, what you've got is a sort of operations research application within the aircraft industry. So this is intended to demonstrate that these probability regression type models do have very broad application within business and finance. Okay, and in neither case, you could argue, is the main application area finance, but certainly both of these stem from genuine business analytics problems, and there is certainly a broad range of application of these types of models. For instance, the first set of problems that we will look at have regulatory significance to problems within the UK water and electricity industries when you have regional monopolies. So even though we're starting with this big data example, some background maths and programming is really important here. So to fit probability regressions in R, you need to be aware of some of the background mathematics and the data structure. So you really got to think about how the problem at hand works. So in terms of the background maths, technically speaking, logistic regression and probability regression models are examples of something called generalized linear models. There's a reference to my textbook there. This means that the R command used is GLM for generalized linear model. So you don't need to know the background mathematics, but the background mathematics does inform the R code that is used, and it makes it easier in terms of the R programming if you're aware of at least some of this backstory. Then in terms of the R programming, remember you've got to tell R exactly what you're doing because R is like a robot. So you've got to specify the family of distributions used, in this case binomial, to tell R that you are actually fitting probability regressions, not just normal regressions. You have to also tell R what link function you are using. So the default, the natural one to use, is the logit model, but if you don't specify this, then the logit model is the model that R will fit. If you want to fit a probit model, you'd actually have to explicitly get R to fit this. Okay, and just wanted to say here, these are all bits of R syntax. It's important to be aware they do have a mathematical origin and underpinning. Some further considerations that are important here. So to fit a binomial generalized linear model in R, these probability regression models, you need the data organized in columns of successes and failures. And this can look a little bit weird when you first see it, but it should become more natural with increased practice. And then I ought to say here that strictly speaking, binomial models are formulated for occasions where you only have two categories. So typically things like yes, no, successful, unsuccessful, male, female, etc. So what you normally have is sort of two categories and only one equation needed to describe that. So our big data example with three categories, high, low and medium, can be modelled using 3 minus 1, which equals 2 equations. And then what you can do here is fit the third equation, but it should be redundant. And this is a sort of thing that isn't worth doing mathematically, but it's still worth doing in practical terms here, because what you should get is that this third equation is just redundant, and if you can verify this, this gives you a way of checking informally in practical terms that the rest of the conclusions are still in order and that you do actually understand the problem as well as you think you do. Okay, and these further considerations here just show that you have to be very deliberate, very precise whenever you've got computational problems at hand. So this data structure then is really important to get right in R. This can look harder than it really is when you first see it, okay, but it should become easier with enhanced practice. So in order to fit these probability regression models, technical term would be a binomial generalized linear model. In R you need the data organized in terms of columns of successes and failures. So the R coding is deliberately named, and the R command you need to do this is cbind, which just means literally binding the columns together. So this has the effect of binding the required counts of successes and failures together. So for our big data example in R, you have sort of 3 separate ways of doing this, where you're clubbing together the values for the high scores from the survey, the low scores, and the medium scores. And the way that you do this would be, so for instance, the first case, y high goes to cbind of the high and 1 minus high. This would give you the columns of successes and failures. And then for the low values from the survey, cbind low and 1 minus low would again give you this binding together the columns of successes and failures. And it works exactly the same way for the third category, cbind medium 1 minus medium, again gives you this binding together of the columns of successes and failures. Normally the fit binomial generalized linear models in R then, the basic set of commands are very similar to what we saw before in the last lecture. R is like a robot, it will do exactly what you tell it to do, nothing more, nothing less. And within this you've got this very deliberate 2-step process. So the first step is a computational step, and the second step is a summary step. Okay, so for the first step what you've got is a generalized linear model, y high related to region, that's what the twiddle sign means, family equals binomial, tell it that you want it to do a probability regression model, and then in the second case specify you want to fit a probit model, it will fit a logic model automatically. Call it something sensible, no room for whimsy here really, so what I've said here, high1.glm, high2.glm, and in the second step what you're doing in order to summarize these results, so what you've got in the line immediately below the third bullet point, summary high1.glm, that's got to match exactly what you called the thing above. Similarly, summary high2.glm, that's again got to match exactly what you called the thing above. And there is a certain subtlety here in terms of the interpretation. What you should get when you have a practical problem is that similar models should give you similar answers, so in this way they should serve as a cross-check of each other in applications. Okay, it's easy to miss this if you just think of this as purely a maths problem. So what you've got here is the table of t-statistics, which is a natural thing to look at, and again works exactly the same way as we saw before in the last lecture for the regression models. So the interesting part of this table is the second row downwards, and what you tend to do is work it out working from right to left, and then write it down in the Queen's English working from left to right. So what you normally would do in terms of the assessment of the module is look for p-values that are less than 0.05. Here there aren't any. And then the next thing to look at is if there are any p-values in this sort of corridor of uncertainty. So p-value bigger than 0.05, less than 0.1, marked in R by this dot. And so the second line, you've got a value here that's in this corridor of uncertainty. So this value here, 0.0539, borderline, significant, and negative. And so working from left to right, writing this down in the Queen's English, the coefficient of the London Essex region is negative and borderline statistically significant, and usually the best way of saying this would be weak evidence, p equals 0.0539. Those in the London region may be less likely to give a high score, precisely because this coefficient is borderline statistically significant and negative. Probit model, so it should work very similarly. So again, the table of t-statistics, you want to look from the second row downwards, work it out going from right to left, write it down in the Queen's English going from left to right. So there's nothing here, the p-value less than 0.05. The next best thing, you've got one p-value there, 0.0538, marked again by the dot at the bottom, which is borderline statistically significant. So an example where the p-value is bigger than 0.05 but less than 0.1. So work it out going from left to right. So the coefficient of the London Essex region is negative and marginally statistically significant. This would usually be interpreted as weak evidence, p equals 0.0538. Those in the London region may be less likely to have a high score, precisely because this coefficient for the London-Essex region in the second row is marginally statistically significant and negative. And the other thing to watch for here in terms of the interpretation, remember this isn't just an exercise in applied mathematics. You've got two similar models here giving you similar interpretations for the same data set. So it says there in the second bullet point, the probit model leads to the same interpretation as a logic model, and this is significant in applications, and again expect to find similar answers from similar looking models. I wanted to give you some examples here of numerical calculation here, which should present proof that similar models should give similar answers. Okay, so from the previous set of regression results from 2 slides ago, from the logic model, what you would do is set log of the probability of a 1 minus probability equals to the regression bit. So I said there log, but I mean ln. So you get that the log of the p over 1 minus p should be equal to 0.931915. Take the exponential of this. So p over 1 minus p equals the exponential of the regression bit, which gives you 2.539367413. And then the probability is the exponential of the regression bit over 1 plus the exponential of the regression bit. And as it shows there at the bottom of the slide, you should get in this case probability of 0.717. So this is a nice probability in the sense that it is both positive and less than or equal to 1. Okay, so if I tell you that some probability is 0.717, it's not obvious that I've lost my marbles. If in contrast I told you the probability was 1.2, then at the very least it should be very suspicious. But happily this seems to give us a reasonable estimate of this probability. Of this slide is that you should get a similar estimate to the previous slide. Again, similar models should give you similar numerical answers, which should give you some confidence in terms of the reasonableness of the numbers that come out at the end of it. So what you would do for the probit model is set z to the minus 1 of the probability equals to the regression bit. Then if you're doing this by hand by tables, you would just keep this number to 2 decimal places. Isn't worth keeping this number to more decimal places because you've got limited resolution of the table. So if you're using tables rather than a computer package, you've got some inherent rounding error there. And then what you would do to calculate the probability will be the z transformation of this number there, 0.58, and you should get a similar answer to the previous slide, 0.71904 in this instance. Now you do actually get some difference here between the two different estimates, although that difference is very slight. That difference is caused by rounding error used in this instance because we're using normal probability tables. Okay, you could get more similar answers if you were using R and the function pnorm at the bottom of the slide there. I wanted to keep it here though because you wanted originally detailed examples of these hand calculations. Now, these probability calculations work the same way for the different categories. So again, very similar to what you've seen before. R is like a robot, it will do exactly what you tell it to do, nothing more, nothing less. And what you've got here is this explicit two-step approach. So the first step is a computational approach, then the second step is an explicit summary step to produce you output on the computer screen. So the R code works exactly the same as before. So you've got a generalized linear model, in this case y low related to region, that's what the twiddle sign means. Family equals binomial, telling R to fit a probability regression model, and in the second case to fit a probit rather than a logic model. Call the thing something logical, limited room for whimsy here. Here we've called them low1.glm and low2.gln, and then the summary step below that has to match the explicit name above. So that low1.glm has to match the name given in the first set of commands, and below that summary low2.glm, that low2.glm has to explicitly match the name above as well. And again, expect to find in applications similar models giving you similar answers, so you can be more confident in terms of the interpretation and the numerical estimates if that holds. Similar models giving you similar answers to the same data.